Start applying the things we've discussed and start applying stoichiometry to it, specifically solution stoich. So first up, write the equation for the precipitation reaction between an aqueous solution of potassium carbonate and an aqueous solution of nickel 2 chloride. And that's what's shown in the picture is what it would look like. First up, write the formulas of the reactants. So potassium carbonate, I know potassium is group 1 alkali metal, so when it forms its cation form, it is a cation, it's a metal, so it's positively charged and it has a +1 charge. So K plus. Carbonate is one of my polyatomics I have memorized, CO3 2 minus. So that means K2CO3 is potassium carbonate because I need 2 potassium ions to charge balance 1 carbonate ion. I also have nickel 2 chloride. Nickel 2 tells me that the nickel has a +2 charge. Chloride is one of my halogens. It is group 17. Group 17 halogens always form anions. They gain electrons and they gain 1 electron to form a -1 charge. So I need Ni and Cl2. I need 2 nickel or 2 chlorides to balance out 1 nickel charge. Determine the possible products. Crisscross. Again, cation from one to anion from the other, cation from one to anion of the other. So I get NiCO3. Again, remember that Ni is a +2 charge and the carbonate's a -2 charge. So it's kind of like I'm taking these guys away, putting these two together, and then I'm putting these two together. And KCl. So determine the possible products and write the formulas of those products. Okay. Examine if the products are soluble or not. If both products are soluble, it is a no reaction. Nothing will happen. Nothing's going to form. But if one of them is insoluble, it's the formation of that insoluble product that allows the reaction to proceed. So I know that KCl is soluble because potassium salts are always soluble. They're a group 1 salt. But nickel carbonate is insoluble. Carbonates are often not soluble, and nickel is not one of my exceptions to that solubility rule. So I've got nickel carbonate as insoluble and KCl as soluble. Write the phase notation and balance the overall reaction. K2CO3 is aqueous. Again, all potassium salts are going to be aqueous because it's a group 1 salt, plus NiCl2, also aqueous. Chloride is usually soluble. There are some exceptions, but nickel 2 is not one of them, giving me KCl and nickel carbonate. Now I have to balance this. I do need to put a 2 in front of the KCl here because I do have 2 potassiums on the other side and 2 chlorides on the other side, so I do need a 2 here to balance this out. What do I have next? Lead 2 nitrate reacts with cesium sulfate in an aqueous precipitation reaction. What are the formulas of lead 2 nitrate and cesium sulfate? Write the molecular equation and ionic equation for the reaction, and what are the names of the products? Well, if a product is forming, that means something's going to be insoluble here, because otherwise there would be no reaction. So the question is emphasizing to me subtly, but it is telling me there is a reaction happening here. There is something being formed. So let's go through it. Lead 2 means Pb2 plus. Nitrate is NO3 minus. So I've got Pb, NO3, 2. Nitrate salts are always soluble, no exception to that rule, so lead 2 nitrate will also be soluble. Cesium sulfate. Cesium is one of my alkali metals, and so when it forms an ion, it forms a cation. It's group 1 +1 charge, and sulfate is one of my polyatomics I know, SO4 2 minus. So I need 2 cesiums for every 1 sulfate. But cesium is group 1, which means it is always soluble. What will this form? This is a double displacement reaction, so swap partners. Cation of one to anion of the other, cation of one to anion of the other. I'm going to form PbSO4. So again, if you think about your ions up here, I've put this cation with this and this cation with this. Now I've got Pb2 plus and SO4 2 minus. They charge balance each other, so I don't have to put multiple of anything. And then CsNO3 are both +1 -1 charge, so they cancel each other out as well. Now I have to think about solubility. I know nitrate salts are always soluble, and I know cesium is part of group 1, so group 1 salts are always soluble as well. Lead 2 sulfate, sulfates are not always soluble, and lead is not a soluble sulfate. So this will be insoluble. This is your molecular equation. Now it's asking to also write the net ionic equation. Here's a shorthand for you. You can write out the complete ionic equation and then the net ionic equation if you would like to, and that is perfectly fine. I have no issue with that. But I will tell you, remember what the net ionic is doing. The net ionic equation is showing you the driving force of the reaction. The driving force of this reaction is the formation of the PbSO4, the lead 2 sulfate. So PbSO4, so what forms that? Well, my Pb2 plus and my SO4 2 minus. And now you have your complete net ionic equation without having to go through the total ionic. I can very quickly look at this and say, oh, you know what? My spectators are my nitrate ion and my cesium ion. They're not in that net ionic. The last thing I need is the names of my products. So your products here, this is called lead 2 sulfate. Lead has multiple oxidation states. So we have to emphasize which one it is, and it is the lead 2 plus state, lead 2 sulfate, and cesium nitrate. Again, cesium ions and nitrate ions may be spectators, but if I took the water away, I would have cesium nitrate be formed. What's next? What volume of a 0.1 molar magnesium chloride solution is required to precipitate all of the silver from 10 mils of a 0.5 molar silver nitrate solution? Okay, I've got a magnesium chloride solution. I know that's soluble because I know my solubility rules. I have got a silver nitrate solution. I also know that's soluble because I know my solubility rules. And I know nitrate salts are always soluble. I know chloride is usually soluble. Magnesium is not an exception to that. I'm going to swap my ions here. Cation of one to anion of the other. Cation of one to anion of the other. Again, if you have to write it out, that's fine. This is the same as Mg2 plus and 2 Cl minuses, Ag plus, and NO3 minus. So what this means is this magnesium is going to hang out with nitrate. The silver is going to hang out with the chlorides, but I'm going to have to do some balancing here. I'm going to need 2 of those nitrates to balance out the magnesium. And nitrate salts are always soluble, so this is aqueous. And I only need 1 of those chlorides to balance out the silver, but silver chloride is an insoluble salt. Definitely need to balance this thing. I have 2 chlorides on the reactant side, so I need 2 on the product side. I have 2 nitrates and 2 silvers on the product side now, so I need 2 nitrates and 2 silvers on the reactant side. So now my reaction is balanced. Okay, now that we've got a balanced reaction, we can go ahead and solve the question. I want to know the volume of magnesium chloride. Now, I'm going to go to milliliters. That's probably what you're going to need. If it doesn't specify, you could argue leaving it in liters. But I'm going to go to milliliters just because there's no reason we shouldn't be converting all the way to mils. That's what we're most likely to use in the lab. So number of milliliters I need of the magnesium chloride solution. I'm starting off with my 0.500 moles of silver nitrate for every 1 liter of solution. I don't have an entire liter of silver nitrate though. I only have 10 mils, which is the same as 0.0100 liters of my silver nitrate solution. So again, that takes into account how much you actually have based on the volume of the solution you actually have. This cancels out my liters of solution, giving me moles of silver nitrate. Now that I'm in moles of silver nitrate, I can go ahead and use my balanced reaction. I see that I've got 1 mole of magnesium chloride consumed for every 2 moles of silver nitrate consumed. So that cancels my moles of silver nitrate, and I'm into moles of magnesium chloride. I don't want moles of magnesium chloride though. I want volume. And I have a 0.1 molar solution here. Remember, that means 0.1 moles of MgCl2 per 1 liter of MgCl2. But I can write that conversion, that's a conversion factor, so I can write that the other way as well, meaning I can write 1 liter of MgCl2 over 0.100 moles of MgCl2. And I need to write it that way because I need to cancel my moles out of my numerator and get me into volume. Now I've got liters. I know that there's 1,000 milliliters in every 1 liter. And this final answer here, so this just cancels out my liters to milliliters. My final answer here is 25.0 milliliters of the magnesium chloride solution I have. Notice here I had 3 sig figs. Here I had 3 sig figs. This is exact. Here I had 3 sig figs, and this is exact. So my final answer had 3 sig figs. And that's how we do solution stoich. Just like what you guys have already been doing with stoichiometry, we're just adding another dimension to it by putting the solutions in place and by making you figure out your balanced reactions. Think about this one. What mass of calcium carbonate is formed when 25 mils of a 0.120 molar calcium nitrate solution is mixed with 30 mils of a 0.110 molar potassium carbonate solution? I recommend writing out that reaction first. So I've got calcium carbonate, and that's being formed. So that is a product. So it's even helping me out. Tell me one of my products. That's cool. Let's see. I'm starting with calcium nitrate and potassium carbonate. So calcium nitrate, calcium is Ca2 plus. It is an alkaline earth metal. So when it forms an ion, it forms a +2 charge. It's group 2. Nitrate is NO3 minus. So I'm going to need 2 nitrates for every 1 calcium. So Ca NO3 2. Now all nitrate salts are soluble. And potassium carbonate. Potassium is an alkali metal, group 1. All group 1 forms +1 cations. Carbonate is CO3 2 minus. So I'm going to need 2 potassiums for every 1 carbonate. K2CO3. All potassium salts are soluble. These two are going to react, and it even tells me one of my products. It tells me I'm going to form calcium carbonate. So my calcium ion is going to hang out here with my carbonate, which means my potassium must go to my nitrate. CaCO3, and that's going to be solid. Carbonates are not very soluble, and they're not soluble with calcium. And I'm going to have 2 moles of KNO3. And now my reaction is balanced. Write down what you're told. Let's see, you have 25 mils of a 0.120 molar solution of calcium nitrate, and you have 0.11 moles, 110, or sorry, 0.110 molar and 30 mils of a potassium carbonate solution. So hopefully you recognize what this means. You are given information to get moles of each species. That means this is a limiting reactant example. You have to figure out what your limiting reactant is. So first thing I'm going to do is I'm going to convert everything I have to moles. So the number of moles, calcium nitrate, I have 0.120 moles of calcium nitrate for 1 liter of solution of calcium nitrate solution specifically. And I have 25 mils of it, which is 0.0250 liters of solution. This gives me 0.00300 moles of calcium nitrate. I am not picky if you put this in scientific notation or not. As long as you write it correctly, I don't care what you do, okay? Makes no difference to me. And do the same thing for the number of moles of potassium carbonate. I have a 0.110 molar solution, so 0.110 moles of K2CO3 in every 1 liter of the potassium carbonate solution, and I have 30 mils of this solution. This gives me 0.00330 moles of K2CO3 in my solution, or 3.30 10 to the minus third moles, whichever way you want to write it. Now I have to figure out what my limiting reactant is. And I'm going to shrink these down because I'm going to need space. So to do that, I'm going to just pick one randomly, and I'm going to say, okay, well, how many moles of calcium nitrate do I need to react all of my K2CO3? I have no idea. I know I have 3.30 10 to the minus third moles of the K2CO3, and the balanced equation is a 1-to-1 ratio, which means that 1 mole of calcium nitrate is required to react 1 mole of K2CO3, which means I would need 3.30 10 to the minus third moles of CaNO3 or calcium nitrate to react all of the K2CO3, all of the potassium carbonate I have. And then I ask myself, do I have enough? And the answer is no, I don't have enough. So what does that mean? Well, that means that your calcium nitrate is your limiting reactant and your potassium carbonate is your excess reactant. But this allows you to answer the question. That means that your calcium nitrate will control how much of your calcium carbonate can be produced. So you're going to use your moles of calcium nitrate to answer the question. The number of grams of calcium carbonate produced will be dependent upon those moles of calcium nitrate you found initially. So 3.00 10 to the minus third moles of calcium nitrate. 1 mole of calcium carbonate is formed for every 1 mole of calcium nitrate consumed. Convert that to grams because I don't want mass, or I don't want moles, I want mass, I want grams. Mass is, when you see the word mass, it means grams unless otherwise stated, but it definitely does not mean moles because moles is a number, not a mass. Calcium carbonate weighs 100.1 grams per mole. And this gives me an answer of 0.300 grams of calcium carbonate. So you've just done a limiting reaction example with solution stoich. Good job. What's next? Write the net ionic equations for the following reactions. First up, I have a strong acid and a strong base, okay? When you have a strong acid and a strong base, all that's going to happen here is it's going to form water. An acid and a base form salt plus water. So it's going to form calcium nitrate, which is soluble, and a mole of water. or sorry, in this case, 2 moles of water because you got to balance the reaction. 2 moles of water. You want to balance this thing out, put a 2 in front of here. For two nitric acids are required to balance out 1 calcium hydroxide. But whenever you see strong acid and strong base, not acid base, but strong acid and strong base, it's always, net ionic is always going to be H plus, OH minus, giving you H2O. Again, if you don't trust me, write it out. 2HNO3. Reacts with 1 mole of calcium hydroxide. I'll show you how we get down to that ratio in a sec of what I just wrote. This reacts to form calcium nitrate and water. Sorry, this one's going to form 2 moles of water. Now, my spectators here are your calcium ion and your nitrate ion. When this splits apart, it forms 2 H pluses, 2 NO3 minuses. And ions only exist in aqueous solution, so they got to be AQ for the phase. Calcium hydroxide is a strong base, so it also splits apart, forming calcium ion and 2 moles of hydroxide ion. I'm going to run out of space here. Calcium nitrate splits apart, forming calcium ion and 2 moles of nitrate ion. And then 2 moles of water are formed. If I take out my spectators here, I have 2 moles of nitrate and 2 moles of nitrate. 1 mole of calcium ion, 1 mole of calcium ion. Notice what's left behind here. Get rid of this noise down here. What's left behind here when I remove the spectators is 2H plus 2OH minus, giving me 2H2O. But your balanced reaction, you want the lowest ratio. So H plus, OH minus, and H2O. That's the driving force of a strong acid, strong base. Formation of water every time. You should be also able to draw that out by picture though and describe what's happening. So I didn't mean to erase that one. I meant to shrink that one. 1 second. I'm going to move this up here just to get out of the way for a sec. So this is what I mean by drawing it out, what's actually happening. Let's say you had a solution and you had them, let's say you have them separated at first, okay? On one side, you put your HNO3. So you've got some H plus ions floating around, and you got an equivalent amount of nitrate ions floating around. And then you've got some calcium hydroxide. And for every 1 calcium, you have 2 hydroxide. Let's say you take out that barrier and you let these things mix. The calcium ion is going to find 2 nitrates. And if there's not enough water to stabilize them, they'll hang out, but they're not actually going to form anything because as long as there's water around, they're going to keep staying in solution. If I take the water away, they will further associate. So 1 calcium, 2 nitrates. But the bigger deal is the water and hydroxide. These two really like each other, and these two will react to form water. So in this system, what's going to happen here is the formation of water, hence your H2O liquid here. And then you're going to have calcium and nitrate ions still floating around in solution. So waters will form. There'll no longer be ions in solution. It will just be more water in solution because it's already in water. It'll just make more water. And then these ions will just keep floating around as spectators like they were to start. Okay, I cannot separate those things back out. And they'll just keep floating around as long as there's water present to support the ions in solution. That's what we're trying to get you to see when we're having you do these reactions. Let's talk about the next reaction. The next reaction is not a strong acid, it's a weak acid. So this is a strong acid, and that's what the net ionic was. Let me just erase this mess. Put this back here. Okay. When you have a weak acid, it does not dissociate 100% in solution. It only breaks up a little bit. So your net ionic here, it will still form some water, but you're going to still have that weak acid present. The only spectator now will be the potassium ion. So again, spectators here are the nitrate ion and the calcium ion. Spectators here will just be the potassium ion. There won't be a second spectator. This is going to form acetate and water. And then the last example shown is a weak base in solution. So methylamine is a weak base. Bases accept protons to form OH minus in solution. So that CH3NH2 reacts with water. And right now we're drawing them as single-headed arrows. What we're going to see is these are actually equilibrium arrows here, okay? I won't be too picky about that right this second, but in Chem 2, it's a very big deal. It's going to form hydroxide, and it does that by accepting a proton. So plus CH3NH3 plus, it gained an H and a +1 charge to it. So it has an overall plus to the species as well. But that is, so strong acid, strong base, a weak acid with a strong base, and a weak base with water in solution. What's here? The titration of 10 mils of HCl solution of unknown concentration requires 12.54 mils of a 0.100 molar sodium hydroxide solution to reach the endpoint. What is the concentration of the unknown HCl solution? Let's see. We've got HCl, strong acid, reacting with NaOH, strong base. Swap your partners, cation with anion, cation with anion. Acids and bases always form water and salt. This case just happens to be NaCl for the salt. It's a 1-to-1 ratio here. So what I want is the concentration of the HCl, which is the same as the moles of HCl over the liters of the HCl solution. I can start with either the volume of sodium hydroxide or the molarity of sodium hydroxide. I personally start with the molarity. The molarity is 0.1 molar, which means I have 0.100 moles of NaOH in every 1 liter of NaOH solution. I've used 12.54 mils of it, but I need to convert that to liters. So 0.1254 liters of the NaOH solution. Right now, if I stopped, I would have moles of sodium hydroxide. I don't want moles, I want concentration of HCl. But because I'm in moles, I can go ahead and use my balanced equation. I know that 1 mole of HCl reacts with 1 mole of NaOH. So now I've got my numerator. Now I just need to get the denominator. And I do that by dividing this whole thing by the volume. So just 1 over, I have a 10 ml solution, so 0.01000 liters of HCl solution. Calculate that out, and it gives me a numerical value of 0.125. And again, that is moles of HCl per liters of HCl solution, or 0.125 molar HCl. What do we have next? A 15 ml solution of barium hydroxide is neutralized with 30.5 mL of 0.2 molar hydrochloric acid. What is the concentration of the original barium hydroxide in the solution? So I've got barium hydroxide. I know barium hydroxide is one of my strong bases. Barium's also an alkaline earth metal, so it's a +2 charge. Hydroxide is OH minus. I need 2 hydroxides for every 1 barium. Strong bases are always soluble. I'm going to react this with HCl. Swap partners here. Barium to the chloride, the proton to the hydroxide. So I form water and BaCl2. I need 2 chlorides for every 1 barium. I do need to balance this. And so because I have 2 chlorides, I'm going to need 2 HCl's. It's also causing me to form 2 waters. So I want the concentration of the barium chloride, or barium hydroxide. So I want the number of moles of barium hydroxide that I had at the start per liter of the barium hydroxide solution. My HCl was a 0.2 molar solution, which means 0.200 moles of HCl for every 1 liter of HCl solution. It told me I used 30.5 mils of the HCl. In liters, that's 0.0305 liters of HCl. Again, if I stopped right now, I'd have moles of HCl. So now I can go ahead and use that balanced equation. 1 mole of barium hydroxide reacts with 2 moles of HCl. So my moles of HCl have canceled and I've now got moles of barium hydroxide, but I don't want just moles, I want moles per liter. So I'm going to say times 1 over that volume in liters, 0.0150 liters of my barium hydroxide solution. This gives me a numerical value of 0.0203 molar barium hydroxide. Again, you can also write that as moles. Hold on 1 second, I'm checking my calculator. 0.2 times, I think I wrote down wrong. 0.0305 divided by 2 divided by 0.015. Yeah, that's what I thought. It looked a little weird to me. That should not be 0.02. It should just be 0.203. I wrote that down wrong in my notes, so I apologize about that. It should be definitely 0.203 molar. Still 3 sig figs either way, but I want to make sure we have the right concentration written down. So again, molar here means the same as moles per liter. What do we have next? Sodium hydroxide reacts with nickel 2 nitrate. We have A, B, and C here. First, so A, B, and C. First up, what is the balanced chemical equation? Well, sodium hydroxide I know is NaOH. I know it's one of my strong bases, so it's aqueous. Nickel 2 means Ni2 plus. Nitrate is NO3 minus. So NaOH, aqueous, plus Ni, NO3 2. I need 2 nitrates for every 1 nickel. And then I'm going to swap partners to figure out what's produced. So the sodium is going to go to the nitrate, NaNO3. Sodium is +1 charge, nitrate's a -1 charge, so 1-to-1 ratio. And nickel to hydroxide. For every 1 nickel, I need 2 hydroxides. Now, I know sodium nitrate is soluble. I know most of my hydroxides are insoluble. Exceptions to this is my strong bases, but this is not a strong base, which means this is also insoluble. So I've got the reaction. Now I just need to balance it. Let's see, I've got two nitrates on the reactant side. I need two nitrates on the product side. Now I have two sodiums on the product side. I need two sodiums on the reactant side, and I have two hydroxides on each side, and my reaction is balanced. Cool. What are your spectator ions here? How can you tell? Well, the driving force of the reaction is the formation of your solid species. So that means that anything that's not in the driving force of that is a spectator. That means my spectators here would be Na plus and NO3 minus. Because notice here, this means I have two Na pluses and two OH minuses. This means I have one nickel 2 plus and two NO3 minuses. This means I have two Na pluses, two NO3 minuses, and this means I have one nickel 2 hydroxide. What I see looking at this is I've got two sodiums and two sodiums on each side, and two nitrates and two nitrates on each side. So the sodium ion and the nitrate ions are my spectators in this reaction. And part C, if 28 grams of sodium hydroxide reacted with 0.525 liters of a 1.25 molar nickel 2 nitrate solution, how many grams of precipitate would form? Okay, I'm going to erase these out of the way so I can write this down. I love the scribble function when I have it turned on correctly. Okay, what I see here is I've got 28.5 grams here, and I've got 1.25 molar here, and 0.525 liters. Hopefully you recognize it, but that means that this is in fact a limiting reactant example, which means we're going to need some space, and I do not currently have space. So we're going to use the space down here. We're going to copy this down, and I'm probably going to have to go to white paper for you guys, because that's probably going to hurt your eyes. So let me change the template on this quick so that I don't completely slaughter your eyes on it and use white. Okay, so I do have a limiting reactant example here. I need to figure out what my limiting reactant is to answer the question. Multiple ways to do this. Truthfully, I'm just going to go ahead and calculate for both of them and see which one makes the least amount, because for me right now, that seems like the easiest process. So let's show you what I mean. How many grams of nickel hydroxide can I produce if I use up all of my nickel 2 nitrate? I have 1.25 moles of nickel 2 nitrate in every 1 liter of solution. And I have 0.525 liters of that nickel 2 nitrate solution. If I stopped right now, this cancels out my liters of nickel 2 nitrate solution, because that is what this is down here. And I would be in moles of nickel 2 nitrate. When I look at my balanced reaction, I see that 1 mole of nickel hydroxide is produced for every 1 mole of nickel 2 nitrate consumed. I'm just going to go ahead and calculate all the way to grams, just because at this moment in my life, it seems like the easiest process. So 92.71 grams of nickel hydroxide for every 1 mole of nickel hydroxide. This gives me 60.84 grams of nickel 2 hydroxide that could be produced. But again, that's just based on one reactant. I don't know what the other reactant is going to tell me, and that's what I need to figure out. Which one gives me the least amount? So let's check it. How many grams of nickel 2 hydroxide could I produce if I reacted all of my sodium hydroxide? I've got 28.5 grams of NaOH. I know 1 mole of NaOH weighs 40 grams. Added that up from the periodic table. Looking at the balanced reaction, 1 mole of nickel 2 hydroxide is produced for every 2 moles of sodium hydroxide consumed. Just kind of reminding you guys, cancel your moles here, and that's how you got your grams up here. Down here, same idea, grams here, moles here. Now we're trying to cancel out into grams, get our grams of nickel 2 hydroxide. So 92.71 grams of nickel 2 hydroxide for every 1 mole. Alexa, stop. For every 1 mole of nickel 2 hydroxide. So again, getting me into the grams that I'm interested in. And this would produce 33.0, I'll fix my sig figs above in just a sec, 33.0 grams of the nickel hydroxide. So 3 sig figs here, 3 sig figs in final answer, 3 sig figs here and here, 3 sig figs in my final answer. But now this is what I'm looking at is these two numbers here. These are the two possible answers. So this is another way you can do limiting reaction examples. You look at these two numbers and you say, which one is smaller? The one that's smaller is the most that can be produced. This is telling me, this first one is telling me that if I use up all of my nickel 2 nitrate, that I could produce 60.8 grams of nickel 2 hydroxide. This one's telling me if I use up all of my sodium hydroxide, I can only produce 33 grams of nickel 2 hydroxide. So therefore, NaOH was my limiting reactant. And to answer the question, I can only produce 33 grams of the nickel 2 hydroxide. And that's because that sodium hydroxide is going to run out